Nanoparticles generally refers to particles on a scale of around 1 to 100 nanometers. But exactly how small is a nanometer? A nanometer is 10 to the power of negative 9 meters. That's 1 billionth of a meter, or 0.000000001. How do we compare this? The size difference between a nanoparticle and a soccer ball is proportionally equal to the size difference between a soccer ball and the Earth. So now that you get an idea of how small they really are, you will also understand how their size gives its unique properties. One of the most important being surface plasma resonance. Nanoparticles are tiny, and that means their electrons are geometrically constrained, which is opposite of the sea of electrons found in bulk metals. Plasmon resonance is the interaction of these electrons with light. The electron clouds of nanoparticles oscillate as quantized waves, meaning that they absorb electromagnetic radiation of a particular energy. Remember that visible light has wavelengths from 390 nanometers going up to 700 nanometers. Nanoparticles will absorb any waves which have a matching wavelength to their electron cloud oscillations. So what that means is wavelength absorbed determines the color that we perceive. An estimation of the size and thus the color of nanoparticles of a known shape can be obtained by measuring the maximum wavelength from their absorbance spectrum using a spectrophotometer. Radiant energy of selected wavelength is directed at a sample, and this machine measures what wavelength the solution absorbs the most light energy, and then it displays a spectrum. As the size of nanoparticles change, so does the wavelength of the electron oscillation, and thus their plasmon resonance. This means that nanoparticles of different sizes have different maximum wavelengths and appear as different colors. The most commonly prepared silver nanoparticle has a plasmon resonance maximum wavelength of around 400 nanometers and a distinct yellow color. However, the size of nanoparticles can be manipulated in a fairly simple experiment. This involves 5 reagents: silver nitrate, which gives you a source of silver ions; sodium borohydride, an agent that reduces silver ions to solid silver nanoparticles; sodium citrate, a stabilizing agent which acts as a buffer to maintain neutral or weakly basic pH of the solution. Also, the growing silver nanoparticles always have some silver cations on its surface. The citrate associates these ions, making the surface negatively charged and electrostatically preventing the nanoparticles from aggregating. Without its stabilization, reduction of silver ions leads to bulk metals. You also need hydrogen peroxide, which oxidizes solid silver back to silver ions, preventing the uncontrolled growth of nanoparticles and etching nanoparticles into nanoprism shapes. Finally, potassium bromide is needed, which controls the size of nanoparticles. It does this by binding strongly to the silver surface, forming silver bromide, which arrests growth of the silver particle surfaces. The more of it you have, the smaller the nanoparticles become. Smaller nanoparticles means a decrease in the absorbed wavelength, and like we mentioned before, determines the color of solution. Here, the vials on the left contain no potassium bromide, and increased amounts were added. While nanoparticles may be relatively new to all of us, humans have been producing them for a very long time. One of the most famous examples is Lycurgus cup, made by Romans around 2,000 years ago, containing silver and gold nanoparticles. Interestingly, the cup appears green when light is shone on it from the outside, but appears pink when the light is placed inside the cup. Today, nanoparticles are used in medicine, such as dental work and antibacterial applications, manufacturing in the form of antimicrobial coatings for keyboards and textiles, and electronics such as circuit boards.